Welcome to another tutorial from ADA LLC. My name is Aladdin and I'm a senior engineer in ADA LLC, and I'll be presenting our latest software, FRP Buildings. FRP Buildings is a software that designs concrete beams and slabs reinforced with FRP rebars in flexural and in shear in accordance with ACI and CSA guidelines. I will be walking you through FRP Buildings features and solving an ACI 440 example number 3. So this is the main interface for FRP Buildings, the premium version. So we first start by clicking Start and configure our problem. Do we want to use what kind of units? We have US units and SI units, and choose the code that we want to follow, either ACI 440 and ACI 318, or the Canadian code CSA S806 and CSA A223.3. And then we start by picking our material properties. We have the concrete properties, and then we have the FRP properties for both the longitudinal side and the transversal FRP. For the concrete, we can choose our compressive strength and then click the ACI default checkboxes to let the software calculate the E-concrete and the FR, the tensile strength, the epsilon prime C, the maximum compressive stress, the strain at the maximum compressive stress, and the maximum compressive strain in accordance with ACI. And this is what I'm going to do. If you would like to insert your own number, you can just uncheck and insert the number. For the FRP, for the longitudinal FRP, we're going to insert the EF as 6500 or 6500 KSI with the ultimate rupture strain epsilon FU star without any reduction factor or environmental coefficient equal to 0.012, and of course it will be a glass. And we're going to put the same inputs for the transversal FRP. For the EF, or the modulus of elasticity, is 6500, and for the epsilon FU star without any reduction is 0.012, and it's also glass FRP. For the exposure condition, both codes, ACI and CSA, allow for interior and exterior. In CSA, it's called interior exposure and exterior exposure. In ACI, it's called concrete not exposed to earth and weather and concrete exposed to earth and weather. In our case, we're going to use concrete not exposed to earth and weather. And then click the geometry part, the geometry button. And for the geometry of the problem, we can use a rectangular section, we can use a T-beam section, or an inverted L section. In our case, it's a rectangular section with a width equal to 12 inches and a height equal to 20 inches and a side clear cover of 1.5 and a clear cover of 1.5. And you can see what do we mean by clear cover or the side clear cover or the width or the height in the graphics, and the maximum aggregate size of 0.75 inches. And then for the longitudinal reinforcement, we're going to use a 1-inch bar, and for the transverse reinforcement we're going to use 0.5-inch bar. Other parameters in this interface, we have the KB, which is the coefficient that defines the bond between the FRP and the surrounding concrete, and it ranges between 0.8 and 1.4. 0.8 means a good bond, and 1.4 a lower bond or a weaker bond. And for KB in our case, it's a 1. And for the allowed crack width, we're going to insert 0.028. This is important because one of the aspects that define the design of your section is the allowed cracks, the crack control. So it's in the ACI, it's a crack control. And then we have the deflection, the allowed deflection or the permissible deflection. Both codes, ACI and CSA, have the same cases from case 1 to case 4. Case 1 is L over 180 with a description. When do we use it? Case 2 is L divided by 360. Case 3 is L divided by 480. And case 4 is L divided by 240. Or you can insert your own allowed deflection. And then if you have a high levels of sustained load, you check this box. This will be reflected in the deflection equation according to ACI 440. In our case, we have normal levels of sustained loads, so we uncheck it. And then we choose our beam configuration. You have two options. You can choose from our predefined beams or the custom value beams. For the predefined beams, you have 1 span, 2 span, 3 span, or 4 span options. From the custom beam, you build your own span. So the idea is that you insert the values or the information for 3 or 5 sections, and we reverse engineer it to know what's the structural analysis aspects of this beam and what's the deflection for this beam. In our case, we're going to use a predefined beam, and it's a 1 span, but I want to show you other options. For example, if we have 4 span and we click submit, we have 4 critical options between fully loaded, alternative loading, or two successive loading, and with all the lengths could be different lengths, could be the same lengths for all the span, and which is the span that you are interested in designing. We're going to use, in our case, a 1 span. We're going to click submit, and we have a cantilever concentrated load. We have a simply supported with a concentrated load. We have a cantilever with a distributed load, or in our case, we have a 1 span simply supported distributed load with a length of 10 feet. We're going to choose 10 feet and 1 span simply supported distributed load and click submit. We'll be directed to the loads, and these are the load combinations from ACI 440. If you choose CSA, you will have the load combination from CSA, and then you click. In our case, it's 1.2 and 1.6 live load, but also you can ask the software to pick the critical combination for you. So the software will calculate all these cases and pick the most critical one. Or if you're not interested in following a certain combination, you can insert the total factor load directly. You can insert the ultimate load, the service load, the sustained load, and the dead load. In our case, it's 1.2 dead and 1.6 live. We have 4.48 kip per foot, and for the live load, we have 2.8 kip per foot. These are the loads on the span that you are interested in designing, but in case if you have 2 span, 3 span, or 4 spans, the dead load on the other span will be affecting the span that you are that you are designing. This is why over here in the lower section we insert the dead load that's equally distributed over all the spans. In this section, these are the loads on the loaded span only, the one that you are interested in. And then you click design. Since we have a simply supported case, so we have one critical section, which is the middle section at 5 foot from the support. If you have a continuous section, span, for example, you will have 3 sections, one on the left side of the support, one around the middle, and one at the left, one at the right support. And then for our section, we have the ultimate moment, we have the service moment, we have the sustained load, and we have the design number of bars. We have 5 bars at a depth of 17.5, and the controlling design is creep rupture. For our shear design, the critical location of the shear is at 1.46 foot from the support, and the shear at that location is 35.09. And the spacing for the bar diameter equal to 0.5 inches is 5 inch. And then you can see the ultimate bending moment for our beam and the shear diagram, the ultimate shear diagram for our beam. This is from the interface, and then to see all the details and all the equations and all the steps that the software followed to get you the result, you click report, and an automatic generation, like the software will generate an automatic report with all detailed equation. You just save it, and then I already have it open for you, and this is the report. You have the table of content, we have the design configuration with the inputs, and then we have the sectional parameters input, the material properties, and then which beam we are using, what are the loads on that beam, the structural analysis aspect of the design, and then the FRP flexural design, including the design limitation, the crack control, the creep rupture, strength, deflection, and then we have the FRP shear design procedure, and then we have the results summary and the notations that we use in that report. I'm going to go through the report. We start with the objective, what we are looking to achieve, the design configuration, which unit, which design code, what are the sign convention, and then we have the sectional parameters for the cross section and then for the reinforcement, and then we have the material properties with the equation. Since we checked the ACI default, these are the equation that the software used. And then we have the FRP properties, and then we have the beam configuration. We have one span with a length of 10 and it's loaded. And then we have a dead load equal to 4.48 and a live load equal to 2.8, and this is the combination that we chose. And then we start with the structural analysis. We get the ultimate, the sustain, the service, the dead load, the ultimate shear, and the critical positive moment location. And these are the shear diagram and the bending moment diagram. And then we start our FRP design. What's our limitation? We want our crack width not exceeding 0.028. We want our FRP sustained stress not exceeding 12.5. We want to achieve our strength, and our allowed deflection is 1. Our material limitation, since we have glass and it's not exposed, so the coefficient, the environmental coefficient is 0.8. That makes our strength is 62.4. Our tensile strain is 0.01. And then we go through the gross sectional properties, the cracked condition. We are cracked under service and cracked under sustained load. The first aspect of the design is crack control, and we go through the design steps and all the equations. And then the second aspect is the creep rupture. And then for our strength, we go through our strength. In our case, it's a concrete crushing. And then we go through our deflection with the equation of the deflection, and then we go through our shear and the equation that we used for shear, and then the summary of results. We have a creep rupture the creep rupture control our design. We have an 5 bars at 17.5, an area of 3.95 inch squared. And then we have only the number of bars in each layer. We have 5 bars in the first layer. We have no bars on the second and the third layers. And then we have for our shear, the stirrup spacing for a 0.5 inch is equal. For 0.5 inch diameter is at 6 inches. This is the cross section that we design, and then we have our notation that we used in the report. We hope that you find this software beneficial for your work, and please contact us if you have any question, and visit our website www.ada.app for more details and to download your own demo version to test the software. Thank you for listening and have a good day.